This is Snell Ya Later. In this lab, we're going to be taking a look at the refraction of light. For this lab, we're going to need a refraction tank. So it's a container that can hold different liquids, and on the back side there's a protractor that we can measure the different angles. It's also got a laser on top that's going to shine a beam of light through the refraction tank. Now before we start this lab, we just need to talk about some terms. A vertical line going up and down is what we're going to call the normal. And the reason why we call it the normal is normal means perpendicular, and this line that's labeled as 0 degrees is perpendicular to the change in medium. Now the angle of incident is the angle at which that light beam is going to hit that change in medium. I'm going to measure the angle of incident from where the laser pointer is. Now the angle of refraction is going to be the angle at which it comes out of the change in medium with respect to the normal. Now for this lab, we're going to be testing two different mediums, the air, which is on top, and the water, which is on the bottom. I've dyed the water red so it shows up better on the video. So the first part of this lab, we are going to be going from air to water. I'm going to start the laser out at the 0, and then we're going to go up incrementally by 10 degrees, and we're going to be able to measure the angle of refraction on the bottom of the refraction tank. So this is what it's going to look like. All right, I'm going to gradually increase the angle of incident and measure the angle of refraction. You might not be able to see it that well from there, so what I'm going to do is I'm just going to zoom in, and I'm going to gradually go up by 10 degrees all the way up to 80 degrees. Let's take a look. All right, so now that we've done the part where we're going from air to water, we're now gonna go from water to air. So I'm gonna move that laser all the way down to the bottom so it's shining on the normal, but it's going from the water up to the air. So I'm gradually gonna increment this up by 10 degrees up to 40 degrees, then I'm gonna do 45, and we won't be able to do any after that, and we'll talk about that later. I'm going to go ahead and zoom in and do this experiment so we can get the data. Let's take a look. So now that we've increased the angle of incident up to 45 degrees, now I'm going to increase it to 60 degrees, and we're going to just see what happens. So you'll notice something interesting happens when we're going from the water to the air after a certain point. Now the beam is totally reflected. So now let's take a moment to explain what we're observing in this lab. So for this lab, we have a light beam, which is a wave, and we're changing mediums. Now we know that the medium affects the wave speed. So as we're changing mediums, the wave speed is going to change. Now to find how fast that wave is traveling in that medium, we can use the equation for the index of refraction. Now the index of refraction is equal to the speed of light in a vacuum divided by the speed of light in that medium. The speed of light in the vacuum, which is denoted by the variable c, is the speed limit of the universe. Nothing can be faster than the speed of light in a vacuum. So the index of refraction will always be greater than 1. The higher the number, the slower that light is traveling in that medium. So let's take a look at going from the air to the water. When going from the air to the water, the light is going from a faster to a slower medium. And you can see that the light is bending toward the normal. That's because the light is slowing down. So if we look at the wave equation, we know that it's changing the medium, which is going to affect the speed at which that wave is traveling. Now the frequency comes from the source of the light. That's not going to change. But if we look at the equation for the wave speed, we'll be able to see, well, if the wave speed goes down, that's going to affect the wavelength. The wavelength is always at the whims to the speed of the wave and the frequency of the wave. The frequency is just coming from the source of the light, and it's just this red beam. Now, if we look at the other side where it's going from the water to the air, you can see now it's bending away from the normal. And that's because in this, we're going from a slower to a faster medium. The wave speed is going to increase when it changes the medium. The frequency is still the same because it's still the same light source. I like to think of it as it's going through the medium, I have to have the same amount of waves per unit of time, and that's the frequency. And because the frequency is going to remain the same, the wave speed is going to speed up. That's going to affect the wavelength. And like I said, the wavelength is always at the whims of the frequency and the wave speed. So let's explain why the light seems to bend. I like to think of it as if you're going from a faster to a slower medium, you can see that it's bending towards the normal. So I compare this to pushing a lawnmower on cement versus grass. So if you're pushing it on cement and you're going onto the grass, if you're going at an angle, that front wheel is going to slow down first. So you're sort of going to bend a certain direction, and that's what's happening as you're going from a faster to a slower medium. Now, if you're going from a slower to a faster medium, you can see it's bending away. So because if you're going on a slower, like the grass, you're pushing the lawnmower, you hit the faster, well, it's going to cause you to turn to one side. That is why the light is bending, because it's going in at an angle and certain parts of that wave are speeding up before the other ones. Now, something interesting happens when going from a slower to a faster medium. There's going to be a point at which the light is totally internally reflected. It just bounces off that medium boundary and comes back down. That's because we've passed what's called a critical angle. The critical angle is when the beam happens to go from a slower to a faster medium, and the angle of incident is so much that it's totally internally reflected. This only happens when going from a slower to a faster medium. See, this does not happen from a faster to a slower medium. It only happens the other way around. So now we can use the data that we've collected to actually calculate the index of refraction of water, which is basically saying, well, how fast is that light traveling in the water compared to the speed in a vacuum? In order to do this, we need to look at Snell's law. You can see here, it's just the index of refraction of the first medium multiplied by the sine of the angle of incident equals the index of refraction of the second material multiplied by the sine of the angle of refraction. So let's take a look at the data going from the air to the water. So the index of refraction of air is very close to the index of refraction of a vacuum. The index of refraction of a vacuum is 1. The index of refraction of air is 1.000003. Air does not slow down light very much. So for this lab, we're going to use 1 as the index of refraction for air. That's going to be close enough for our calculations. So let's take a look at the data that we got when we went from air to water. Now we could use any of these angles other than 0. That's not going to work out very well. I'm going to use the angle when we were at 30 degrees. I'm going to do that because the sine of 30 is 0.5. That makes the math a little bit easier. So now we know 3 of the 4 variables in Snell's law. We know the index of refraction for air, which is 1. We know the angle of incident, which we chose, that's 30. And we measured the angle of refraction. So now we just plug it into Snell's law and we can calculate the index of refraction for water. And it's going to be a higher number than 1 because light is slowing down when it gets to water. Now that we've calculated the index of refraction for water, we can now calculate the critical angle from going from water to air. That's that angle at which all of the light is now totally internally reflected. So to do this, we still need to use Snell's law. Now the index for refraction of water is what we already calculated. We're calculating that incident angle, the angle at which it hits that medium change. That's going to be the critical angle. Now the index of refraction for air, like we said, we're just going to use 1. Now the angle of refraction that we're going to use is 90 degrees. So that's just assuming this beam goes up, hits the medium change, and goes 90 degrees. So that's how you calculate the critical angle. And this is what the refraction tank looks like at that critical angle. You can see a lot of it's being reflected, but there is still some of it just above the medium change. Once again, this is Snell Ya Later.